Okay, this is an introduction to acid-base theory. The properties of substances that act as acids and bases have been known for a very long time. You know, back thousands of years, they'd classified some substances as being acidic and some being basic, and they had that based on the properties of those substances, such as for acids tasting sour or for bases tasting bitter. But actually explaining why a chemical acts as an acid or acts as a base, is newer. And there have been different theories that have been proposed, and those theories have developed over time to be broader and include more and more substances. So the original theory had to do just with, it would be called the Arrhenius theory, and had to do with that acids were things that dissociated and gave H plus ions in solution, and bases were things that dissociated to give OH minus ions in solution. And while this is still useful in many situations, it's not going to be used much because it's a little bit limited. It only talks about things in aqueous systems. The one that we're going to use in the SL class is we're only going to use the Bronsted Lowry theory of acid-base behavior. And in this situation, instead of looking at both H plus and OH minus ions for acids and bases, we're only going to look at H plus ions. An H plus ion really is a proton. It's lost its one electron, and therefore all that remains in the hydrogen is a proton. So the Bronsted Lowry theory focuses only on proton transfer. Acids are things that donate or give away protons, and bases are going to be things that accept protons. This is going to be a very useful theory in almost all scenarios of acids and bases. There are a couple of examples of substances that have acidic or basic properties that don't fit into this theory, and for that, the Lewis theory is used. However, this theory is not required in the SL class, so this is an HL topic, just to be clear. So for the SL class, we're going to focus primarily, or actually solely, on the Bronsted Lowry theory. Okay, so to review that, a Bronsted Lowry acid is a species that donates a proton in a chemical reaction. It's a proton donor. A Bronsted Lowry base is the opposite. In a chemical reaction, it's a species that accepts protons or bonds onto a proton. And again, when I say proton, proton equals H plus. Okay, so these are some example Bronsted Lowry acid-base reactions. And so the way that you would look at them and try to identify acids and bases is pretty simple. Look at which substance gives away a proton and which one accepts it. So it might be easiest to see here. If I start with water, when water goes to the other side, it picks up an H plus. It goes from being H2 to being H3, and it goes from having no charge to having a positive charge. Those are two pretty good signs that it has gained an H plus. So in this case, the water is acting as a Bronsted Lowry base. It accepted an H plus, or a proton. Whereas now if I look at the HCl, I can see it starts as HCl, and afterwards it's just Cl minus. It's lost both an H and a positive charge, or one of its charges, so that now it's a negative charge. So HCl is, I can get out of there, it's your Bronsted Lowry acid. It donated a proton. There we go. And just to draw it in to see it a little bit more clearly, right? Here's this H, and then afterwards, right, we've lost H plus, therefore HCl donated H plus. So in order to identify it, you sort of need to look at the change from the reactant over to the product side. And the acid is the thing that loses an H plus, so both a hydrogen letter H and also a positive charge. And the base is going to be something that picks up an H and then also gains a positive charge. Let's see if we can check out these next couple of examples. So in this one, the NH3 turns into NH4 plus. That shows the gaining of an H plus. That means this thing is acting as a Bronsted Lowry base. And the HCl, once again, is giving away an H plus, and therefore it's acting as an acid. So Bronsted Lowry base, Bronsted Lowry acid. They're pretty easy to spot. And one more example. In this one, I see that from this side over to here, that this is picking up a H plus or a proton, and therefore it's the base. And I see that the water is actually giving away a proton, and therefore it's acting as an acid. So this is kind of an interesting idea that water, a substance which we take for granted to be neutral, in a given scenario, it can actually act like a base, or it can act like an acid. So I'm going to skip this last one. It's more of the same. If you think about it, which species above is acting at times as a proton donor, an acid, and at times as a proton acceptor, a base? And the answer to that question was that water is the substance that's doing that. It's not the only substance that can do that, but it is fairly good at acting as either an acid or a base, depending on the scenario. And so there's two different words we can use to describe this kind of behavior. One is we can refer to water as an amphiprotic substance. Think of amphibian as being those types of animals that are sort of partway in the land and partway in the sea. So when you are amphiprotic, it means that you can go both ways with protons. So an amphiprotic substance is a substance that can donate and accept protons, can act as both a Bronsted Lowry, Bl. Bronsted Lowry acid is base. So polyprotic acids are going to be good candidates for being amphiprotic once they have released one of their protons. And we'll come back to this point about polyprotic acids in a later video. There's one other term that could be used to describe this. So we just use the term amphiprotic. We can also use the term amphoteric. It has to do basically the same thing, but a substance that is amphoteric can act as both an acid and a base. However, amphoteric is a little bit of a broader term. If a substance is amphiprotic, like water is, then it is considered amphoteric. It can act as an acid or a base. But some substances are amphoteric without being amphiprotic. And so an example would be like aluminum oxide. Aluminum oxide actually can act as both acid and base, and yet it has no protons on it. So according to the Bronsted Lowry theory, since it has no hydrogen, it can't donate protons and it can't be an acid. So there are some examples, things that fit into that Lewis theory that I mentioned, things that don't fit into the Bronsted Lowry theory that still have both acid and basic properties. And so those would be things that are amphoteric, yet not amphiprotic. So this is the broader term, the amphoteric one. They're very, very similar. They have to do with things that can act as both acids or bases. For the sake of the SL class, it's going to be a lot more important to know the amphiprotic term, the species that, depending on the reaction, can either donate or accept protons. Okay, something you may have noticed is that if you looked at all these reactions, I represented all of them with the equilibrium double arrows. And so that means that not only does the forward reaction take place, but the reverse reaction takes place as well. And so what that means is that the reverse reactions, well, let's see what happens. So as we go forward, we said that in this reaction, this acts as the acid, and this acts as a base. But now if we look at the reverse reaction, we actually have another acid-base reaction taking place in the backwards direction. And so if I think about what happens to H3O plus when it turns back into water, it has to give away an H plus to turn back into water. So in the reverse direction, the H3O plus is acting as a Bronsted Lowry acid. And in the reverse direction, the Cl minus has to gain a proton to turn back into HCl. So the Cl minus is acting as a base. So in the forward reaction, you can identify a proton donor and a proton acceptor, but you should also be able to see that in the reverse reaction, there's also a proton donor and a proton acceptor. Okay. All right, let's try that again. So forward reaction, we saw that NH3 is a base, and it turns into NH4+. And we said that HCl was an acid, and it turns into Cl-. Okay, if you check the reverse out, to go backwards, NH4+ has to then give away the proton to turn back into it, meaning it's acting as an acid. And Cl- has to accept a proton to turn back into HCl, and therefore it's acting as a Bronsted Lowry base. So if you take a look at these two examples, you may notice that whatever acts as a base on the left, it turns into something that acts like an acid in the reverse. Whatever acted like an acid on the left turns into something that has to act as a base in order to return back to the beginning. So let's check that out again. What was a base on the left turns into the thing that acts like an acid in the reverse. What acts like an acid and donates a proton, in the return has to accept a proton. Okay? So this relationship is what's known as a conjugate acid-base pair. These are species in a Bronsted Lowry acid-base reaction that differ by just one proton. The Bronsted Lowry acid in the forward reaction and the Bronsted Lowry base in the reverse reaction are one of these pairs. And the Bronsted Lowry base in the forward reaction and the Bronsted Lowry acid in the reverse reaction are another pair. So there's always two pairs of Bronsted Lowry acids and bases in these reactions. So let's look at the third one here. I'll identify one of them in green. So one way to find them is to look for the two things that are different by just a proton. Okay, so NH3, NH4+, that is a Bronsted Lowry conjugate acid-base pair. The other conjugate acid-base pair is this one. They also differ by just one proton. So I've got NH3 on the left. From here to here, it has to gain or accept a proton, so it's acting as a base. And the NH4+, in order to turn back into NH3, has to act like an acid. Water is giving away a proton to turn into the OH-, and therefore it's acting like an acid in this reaction. And OH- has to accept a proton in order to turn back into water. So conjugate acid-base pair, conjugate acid-base pair. There's always two. There's always one acid and one base on each side of the arrow. Okay, last topic in our introduction to acid-base theory. When you're going to be asked questions about conjugates, and so this is just the example. It says deduce the chemical formula of the conjugate acid of the following. And so how are we going to do that? If you want to find the formula of the conjugate acid, what you need to do is you need to make it act like a base, right? Because after something acts, why didn't I do that? Let's just write this, let's just type it, right? Acts like a base. Or make it, the species, act like a base. And what does a base do in this theory? Well, it accepts an H+. So if we look at these compounds down below, if we want to know what their conjugate acid would look like, then we need to make them act like, we need to make them accept protons. They need to act like bases. So if you think about what is this thing going to turn into, right? If this thing acts like a base, it's going to accept a proton. That means it's going to now have two H's. Everything else about it should be the same, except that because it also gained an H+, its charge should now be 0, because it goes from having a -1 charge to now having a 0 charge. So there's our answer to the question. Make it act like a base by accepting a proton. Okay, we could pick any of these. If I pick this one, for example, a kind of a trickier one, okay, what's it going to turn into? Right now it has one H, so to act like a base, it's going to gain a second H. That's going to be H2. And it had a 2- charge, so now it has a 1- charge. Instead of going back to 0, it only gains one H at a time, and therefore Therefore, its charge just goes up by 1. So I'll leave the rest for us to talk about in class, but in order to identify what something's conjugate acid would look like, you have to make it act like a base. That means you have to make it accept a proton. And now H2SO4 is the conjugate acid of this substance here. H2PO4 1- is the conjugate acid of this right here. Okay, we could do the same thing with this. If they ask you for the conjugate base, then you make the species act like an acid. Okay. We can make it act like an acid. That means we make it donate an H plus away, lose an H plus. So if we go down here, if this thing is going to act like an acid, it has to give away an H plus. So then it's lost that H. So now it's SO4. And instead of being 1-, it's lost another charge. And so now it's going to be a 2- ion. So when this thing acts like an acid, it turns into SO4 2-. So this is the conjugate base. Okay. I'll use this bottom example again as well. Make this red, show that it's our answer. Okay, and so now if I do it again, this is a P. So it had H, PO4 2-. It has to give away that H to act like an acid, and its charge has to drop as it gives away the H. So that's how you would answer, what is this thing's conjugate acid or base? You make it act like the opposite and see what it turns into. And then the following is, which of the following species are likely to be amphiprotic? So things that can both gain and lose protons. Well, first of all, they have to have H's if they're going to be able to act like Bronsted Lowry acids. So the first thing, if they're going to be able to be a Bronsted Lowry acid, they need H. And if they are going to be a Bronsted Lowry base, then it's best if they have a negative charge. They don't have to have a negative charge, but they at least need to have usually a lone pair of electrons. That's going to help them out a lot. It's going to make them good at grabbing protons, good at accepting protons. So if I look down this list, this one is a prime candidate. Actually, in the examples above, you saw it act like both an acid and a base. In one example, we had it gain another H and turn into H2SO4. In another example, we had it lose this hydrogen and turn into SO4 2-. So things that have H's and negative charges are really good candidates for being amphiprotic. So this is another good example of one that could do that. This is another good example of one that could do that. This one is a little more complicated. It's less likely to do it, although you might think it could. The details of that we'll get into when we talk about a little bit more organic chemistry. But basically, this bond between the carbon and hydrogen is a fairly strong one, and it tends not to get broken in an acid-base donation kind of way. The ones that definitely can't are the ones that don't have any H. They can't act like Bronsted Lowry acids. So Br- can't. ClO4- can't because it doesn't have any protons on it. And then ones that are less likely to be bases are ones like this, where H to F, when F usually only forms one bond to get its full octet. It's very unlikely that F would then share another one of its electron pairs with another H and become H2F positive. So it's a little bit harder on that end to distinguish which ones wouldn't do it. And this is sort of it's a challenging type of question, usually on multiple choice. But the best things to look for are ones that have hydrogens and ones that have negative charges both, because then they can both donate and accept protons. So that's our introduction to acid-base theory, identifying acids and bases in the Bronsted Lowry theory, identifying conjugate pairs, and also identifying or figuring out the formulas of conjugate acids and conjugate bases.